Now we talked about uncertainties and how to do experiments, but next step is actually to make a conclusion from it, and then we come to the statistical analysis, and we have to start with some simple model. So because many of the experiments, they are quite complicated, big questions, a lot of complicated combinations of data and everything. So we go for a very simple example, and that is tossing a coin, which probably most statistics class are doing. And so we have this coin, and we want to know if it's fair or not fair. And let's do some experiment, toss the coin 10 times and see, does it provide any result? Or then we want more data. So the question is, if I let someone else toss it 10 times, it's the same as 20 flips. Or if we just do 10 times and then do the shortcut, multiplying by 10, or multiply the data by 10, is it the same as 100 flips? Of course not, but anyway. So, but the question is now, if I buy 10 coins and want to know which ones are the fair ones, what should I do and how should I test those? So the first test is to look at the probability. A fair coin should have a 50% probability of getting heads or tails. And then we need an unbiased flipper, so someone who doesn't bring in some kind of intention into the flipping. So we can assume that it's actually the flipper does exactly the same thing. And then we see what happens. And in that case, the unbiased flipper means that the probability of each flip is the same as the product of each flip is the same as the probability of a flip times the probability of the flip. So in the end, we can get the expected value of all flips should be a half, and that is what we are aiming for. Now again, each flip, as I said, we need an unbiased flipper. So the coin needs to be unbiased, so should not be loaded. And also the flipper, I can imagine if you put the coin always with head up and flip exactly the same, you will have a bias in how you do it. So you actually need a random process already when you select how you put the coin for the flip. And then we get more flips and get more information. And all the random or stochastic variations in coin and flipper, they should cancel out in long run. But again, we have maybe systematic variations which accumulate. And that gives us then our bias and the variance in our flipping experiment. So if you look at the real experiment, then each experiment or each measurement tells us, of course, about our sample, but also about our instrument and how we do the analysis. And more information provide then, here we have the random stochastic variations in sample, instrument, analysis should cancel out, so you get some kind of unbiased distribution around some expected value. The analysis should be harmless, so there should not be much stochastic variation in it. That with some kind of reservation, because there are also algorithms that work in a random way, so they are started randomized, so there is a little bit random variation in it. And then we have the systematic variations that which accumulate in our evaluation. A little bit more complicated model, we come to this flower data set. It's the IRIS data set. It's a quite well-known statistics study. And it covers a number of measurements. It has also different plants and even different species. So we have a pretty wide data set here to work with. And that can be downloaded. The original measurement was done in 1936, so it's actually quite old nowadays. But anyway, it's used a lot in these statistical examples. And what it measures are some anatomical features of the flowers. We have the sepals and the petals, length and width, and then we have different species here. And looking at this, we can do a first inspection using a pair plot, and we can see that some features, they overlap a lot if you combine them. So for example, the sepal length and width, they overlap quite a lot, while other ones, they separate pretty well. So this gives us a first indication how to compare different things. And one way of telling how overlapping the data is to use the intra-class correlation coefficient. And it tells how similar data is within a group, and also if there is compared to the similarity between the groups. And that is, if you have low group similarity, the histograms are very overlapped, and as you know already, overlapping histograms are messed to segment or identify, and also harder to separate. And if you have high group similarity, means that the histograms are separated, and then of course also easy to handle in some hypotheses. Now let's look at the sepal width. That has quite a low group similarity. You can see that these distributions, they are very much overlapping, and that also makes it harder for us to make a conclusion from it. The petals, they are much wider, so the length of the petals is well separated, so it's easier to work with. And now to put a number of that, we can compute this intra-class correlation coefficient, which is given as the this ratio here, where we have SA squared is the averages within each group, and then taking the variance of those. And the SW is looking at the variances of each group and taking the average of that. And those together give us some information that we have this interclass correlation coefficient. If it's 0, all histograms are completely overlapping, so there is no separation between them. And then when it's increasing, you see that there is more separation, then the ICC gets greater and greater. But the most is happening actually when you go well above 0.5. Then you see the most separation, so it's easiest to handle. And let's compute this for different cases. We have the low group similarity for the sepal width, and you can see it's not so separated. Then we get about 50% ICC. And in the case of the petal length, then you have 96% ICC, and it's also telling us that we have a much greater separability between these classes. Now we can start to look at these experiments, and we want to test. First, we have to list some assumptions, and then from these assumptions, we can start establishing a null hypothesis. And in this case, we want to say that both groups are the same. That's the first claim, and then we compute that each of these probabilities are fulfilling this. And you need, for doing this, you need to know the probability distribution usually. And it can be quite complicated to get that right. Now, looking at the decision making, we get this kind of confusion matrix actually. We have the truth in the population, and we have the decision, and then we have the correct answers in retain the null and reject the null is in the diagonal. Then we have type 1 errors, which are the probability is alpha, and then we have type 2, where the probability is beta. So that is reject the null hypothesis, even though it is true. And now coming back to our coin example, now we want to do this hypothesis testing, and our null hypothesis is that the coin is unbiased. And that means we have an average value of 0.5. And now we want to see how many times do we need to flip the coin in order to get this probability. And assuming we have a Gaussian distribution, we have the p-value is the probability here, and we have the unlikely observations in this corner here. And now is the question, what is good enough? How many times do we have to flip the coin in order to reach this probability? That is unlikely. And for that we use the student t-distribution. And it is a go-to method, but it has some assumptions on it. And one thing is you can use it when you don't know your distribution very well. You are relying on the law of the great numbers, that everything sooner or later turns into a Gaussian. But this distribution kind of takes into account that you're not completely sure that it is Gaussian. And it can work with much less data, but the assumption is in principle that we have Gaussian distribution and that the data is also unbiased. And from that, with the help of this distribution, we can now compute the probability of an event being true or false. And the student t-test uses the t-distribution and provides a method to get this probability. And yeah, there we have the unbiased and normal distribution assumptions. And now we want to see if the coin is fair, and the probability that something is not fair, or it's actually the probability to reject a hypothesis, is usually set that it should be 5% of the p-value. And that means we have to flip the coin 5 times and get 5 heads. That's so unlikely that we get this probability of 3%, and that is then deciding that we should reject the null hypothesis. And as we can see here, we can increase our number of tosses. We have again this product series, and we can see that it goes down, 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 and then at some point we have the p-value of 0.05. And that is our flipping point where we decide to reject the hypothesis, null hypothesis. Then we do a lot of experiments. So let's have many friends to do, toss the coin again, and then we have this group probability. And first we say this probability of not getting 5 heads is this, so it's 95%. Or actually, and to the power of number of tosses, and this block here to the power of number of friends, and then we get a probability. And in this case, we see that the probability of 5 heads is first with 1 person is only 3%, but then with 10 it increases. So something is a bit weird here, and even if we have 20, we go up and up. So something is wrong with this equation in our current reasoning. So the problem was that we didn't say that the chance of getting 5 heads was less than 5%. What we said was exactly 5 observations of head, and that all of them are heads, and then the likelihood for fair coin should produce less than 5%. And that is something that happens, and when you increase the number of tests and you need to correct for it. And there we need to look into how to correct for the bias and the increasing number of probability. And the way of doing it, first let's just look at a test where we have multiple observations, we have several variables, and we have 2 groups, all distributed with a uniform distribution between -1 and 1, and we assign groups for it. So we just have a lot of random numbers. Now, all of them come from the same distribution, and now we want to see if it detects some differences. And actually it does. It can happen that you sometimes go below the threshold value, but otherwise it's actually quite likely that it is the same. And if we have a larger table, it's more probable that we now and then find a misclassification. And if we look at it, doing very many experiments, this was running a simulation of more than half a minute. And we can see that if we increase the number of variables in the study, we also increase the number of significant variables. So we need to take this into account. And a way of doing it is, this is just a different visualization. Instead of having the dots, we use the box plot. And you can see that we have a lot of significant, or this number of significant values is increasing. And by adjusting our decision threshold, by dividing the 0.5 by the number of tests, we get a better corrected significant count. And that is our goal. And this is called the Bonferroni correction. It's said to be quite conservative. There are a handful of other correction methods which are less conservative, because if you are doing this kind of correction, you actually have a cost of it. And if you don't do the type 1 error, or you correct to reduce the number of type 1 errors, the cost is actually that you get more type 2 errors. And that is something you have to be aware of. It's the same actually when you do the thresholding in an image. If you want to be sure that you have your regions clean segmented, then you can have to take the cost that you have a lot of misclassifications in the background. So again, we have the same problem here. So switching on to a more practical study. So let's say we have these microscope images of a bacteria colony or cell colony, and we want to compare them. We have a control and we have a treatment, and want to know if they are different. The whole workflow to getting to this point, we already know from the previous lectures. We have all the segmentation and labeling, region properties. Last week I showed the Voronoi tessellation to compute the area distribution, region area distribution, and somehow, oops, something happened. So good. So, and then we got these point clouds. I showed them last week. And here we have 2 clouds. I set them to have 5.5 intensity control in the control and 6.0 in the treatment. And looking at these images, it's not really obvious that they are different, but they come from two different distributions. And now we want to compare them. Also, the histograms look very similar, but let's compare. We try to compute first the ICC, and with these histograms, the ICC tells us that they are more or less overlapping because it's a very low number. So the question is, how well can we actually separate these two? Let's run the t-test to get the p-value. And the p-value we get from this test is 0.16, so 16%, which says we should actually confirm our null hypothesis, that there is no difference between those samples. But there is a difference. So we kind of expect, so we are a bit suspicious. And then we look at our data and we see that there must be very huge outliers in the data, and so large that they are not even realistic. And that is actually what brings us to, that tricks out the t-test. So instead what we do is, with a reasonable threshold, filter our data first. And here I say reasonable because you have to be careful if you cut out data from your measurement. But if you have data points which are, say, 10, 20 times larger, you can quite safely say that they are outliers. So I set here the threshold, all values, areas that are greater than 2, they are rejected as outliers. And then I get a histogram like this, and also with the pruned data, now I get something that I can start compare. And now I get a very small p-value, so that actually confirms that these two samples, they are different. Even though the histograms are very much overlapping, they are told to be different. An alternative test that we can work with is the Kolmogorov-Smirnov test. And it's an interesting test because you don't need to know the parameters of the distribution. You can actually compare an arbitrary distribution in this test to tell if there is a difference between them. And the principle of this test is that you compute the cumulative distribution or the cumulative histogram of the data, and then you measure the distance, the largest difference between the height of these two histograms. And that is the distance that is used to compute a p-value. So here I have two data sets, two very close ones, and here we got the p-value of about 10%. And this one, the p-value is so small that it only shows me zeros. Probably there is some numbers on the lower digits, but right now it's so unrealistic that they are overlapping. And you can also see it here, this dotted histogram below, that they are actually shifted away from each other. So let's try this test on our two cultures. And we see, again, we have confirmed that the p-value is also very low for this data set. So this is an alternative to work with. If you think that the t-test doesn't help you, maybe the conditions for the t-test are not fulfilled, that you have more or less Gaussian data and you also are unbiased, then you may go for something like this. And now we have just compared two samples, and that is maybe good to see the difference between two of them, but there are actually in many of these experiments natural variations with each sample, so it's more like luck if you get two samples that are different or not different. And now we want to see if there is a systematic difference between the spatial patterns across a lot of replicates. So it's time to increase the population that we look at. And now I run again a simulation experiment I don't have the data for doing this, so I have to work with simulations. But anyway, we have the two populations, and the intensity distribution has a Gaussian distribution of the two classes. So they are distributed something like this. And I also have 10 samples in each distribution. And now we want to compare if the Voronoi areas are different between those two populations. So what I have to do is to first create a lot of point clouds. So I generate my starting points with a normal distribution, and then I generate, these are hidden functions actually, they are, if you want to look at the code, it's in the repository. Then I generate a lot of these point clouds, and we want to compare these and looking at the t-test, and the t-test tells us that we get a p-value of 2%, which means we can say that these two, given the data, the t-test tells to reject the null hypothesis that they have the same distribution. So this is a way to compare different treatments. The KS test we can also try, but this time the KS test provides us with a p-value of 16%, which is huge compared to what we got from the t-test. And that means we should actually retain our null hypothesis, so something is wrong. So let's look at when the KS test is actually reliable. And we had 10 samples this time. And the typical recommendation is listed like this, that if you have less than 20, forget the Kolmogorov-Smirnov test. It has very low power, and it's kind of just a random guess if you get it right. If you have larger obvious differences, you can use it for 20 to 50, and then above that you get better and better power in your decisions. So how many samples are needed for getting a good test? Of course, this depends on sample preparation, the experiment type, and that, no, well, you need to have a certain number of data in order to make a good conclusion. But you need to also to prepare all the samples. You have to do the experiments, and also the processing may take time. So you have to find a balance between doing very many experiments and what you need for getting a good conclusion. In the current experiment, I tried to get the p-values when I increased the number of samples. And for low number, we had a pretty high p-value, and then it decreases with the number of samples. So you get better and better certainty that you can reject the null hypothesis. This peak here is, let's call it statistical anomaly, because I only ran one experiment with a random generator, and I was unlucky to get this peak. I tried to run a couple of tests, but every time there was a peak somewhere. So I would have to run like 10, 20 tests in order to get a nice curve here, and I didn't do that. So we can do a lot of conclusions with the help of the statistical analysis, but often we have too little information for the perfect analysis. That means go back to the lab, do more experiments. But the student t-test can help us to make these conclusions, even when we have small amounts of data. And it helps us to reject a null hypothesis on a specific confidence level, which is actually what we want to say. And you should mostly repeat experiments on each point, so you get better statistical foundation for your conclusion. And sometimes you also need a correction to avoid biasing in the conclusions. So this part I can talk about today. So I actually have two parts more. The sensitivity analysis and part about plotting and visualization, but I think I skipped that one for a coming week. So now we switch to a very different topic about looking into sensitivity analysis of parameters in our workflow. So it's more about how you implement and work with your algorithms. So let's start. We have this algorithm where we have a Gaussian filter, and we bring in the data. We have some parameters. We say we have a sigma of 0.5 and a 3×3 neighborhood. Then we do some thresholding at some given value, and we want to do thickness analysis and shape analysis. And here we have three controllable parameters: the Gaussian filter, we have the sigma, and the neighborhood size, and we have a threshold level. And these are the parameters that we can play with and see how sensitive our analysis is to these parameters. So what we do is we sweep parameters, we set the threshold. So that is in principle what we also do in a simple way with the ROC curve. So we sweep the threshold value, and we see how the volume is affected by this on different data sets. And then we see that there is a maximum and a minimum, and then we have to see what happens and in which bound we are working in for different parameters. And then we can see that they are actually looking at the volume using a violin plot. That's a different way of showing it. Then we can also look at the orientation, seeing how the orientation varies. It varies within narrow bound, but still there is a dependence on the threshold value. And sensitivity is also, again, a metric that we need to measure somehow, and it's not easy to really put a value on it. So in control system theory, you usually have voltage in, voltage out, or something like that. Then it's easy to set the parameter. So in principle, it's the change in metric divided by the change in parameter. But in imaging or image processing, it's not so obvious, because you can have the threshold is maybe intensity or gray level, and what you have want as output is volume, and the sensitivity unit is not unitless, but it becomes volume per intensity, which is quite an abstract term. So we have to find something else. So what we instead do is to look at the span of maximum metric versus minimum metric divided by the average metric, and that can give us the sensitivity range for what we do. So if we go back to this plot, we would in that case look for this maximum, this minimum, and then the average, and that gives us the span of how much the sensitivity is. And looking at the sensitivity here, now we can look at the measurements. We have the object count sensitivity, or the object count goes down with the threshold, and then all of a sudden it goes up again. So we have a minimum of object count at some certain measurement, or threshold, sorry. And then we can work with these sensitivity units instead, and then we can see that the count goes down with the threshold, and that interferes, that coincides with two maxima in anisotropy and the volume. And it kind of makes sense, because if you have few counts, item counts, then you should probably have also larger items. So that makes sense. The anisotropy is something that is not really related to the volume. It's how it's working. So sometimes some parameters go down to a minimum, others go up to a maximum. Depends on what kind of metric we are looking at. And another thing is reproducibility in the experiment. So one thing is in the measurement itself. You should have as stable experiment setup as possible. So it shouldn't be, the result shouldn't be depending too much on how you mount the sample. Noise is always the thing. And how you illuminate the sample should also not be affecting your experiment. So if you can get all these things, your measurement is sensitive to these things, it's already good. And the analysis shouldn't have any platform dependence, so it shouldn't depend on which kind of computer you use or even which specific computer you use, but just should run. And then it should be limited to use proprietary or in-house algorithms. It's better to have something that is well defined already, unless you really need to develop an algorithm. But then in that case, it needs to be published and reported exactly what you did. In analysis, you should try to avoid clicking, tweaking, and copying tasks, because that is always prone to errors. And the best way would be even to produce a single script that go from image to result. It needs to be split down into several subtasks, but everything should be called in a single do-all script in the end. So important is to do everything in a disciplined manner. You should have fixed and well-defined steps in your process. And it should be also easy to regenerate results, so you don't have to sit an hour and click and tweak and do stuff. And of course, no magic. It's important that there shouldn't be too many magic unexplained parameters that you need to tune, a bias here, a bias there, some cutting here for make it work. And finally, also very important is to have a documented workflow, that someone else can also understand what you did, and if someone wants to continue working with it, they should know what to do. And the advantage of having this kind of disciplined workflow is that if you have a nice defined workflow, the analysis of 100 samples is the same effort as analyzing a single one. And of course, it requires some initial effort to get there. And still, if you intend to do a mass analysis, it still pays off. But just, watch out that it doesn't happen like this, that in theory, writing some nice code takes a lot of initial effort, and then you have automation. This is the ideal. Unfortunately, what may happen is something like this, that you start writing your code, and then you do some debugging and realize, oh, wrong, and then you have to rethink, and then you spend your whole PhD on developing the automatization. That's not what I promote, but anyway, reality is somewhere between these two. That is the truth. So, in principle, what you want to have is one well-working script for doing your analysis, and few parameters to set and identify. And to do this, we have been working with notebooks. That's good for development, to see how things work. But in the end, if you want to do this mass analysis, it's better to have scripts that you can just call from the command line or something. One example of that is a script looking something like this, where you import your little toolbox that you have developed, and you set a threshold, could even be a command line parameter, and then you run your script. And then with that, you can automate your process much easier, because then you don't have to go in and change for every file you work with. Then you can just say, do this on these files, and it does it for you. So that's a way how you can arrange your work. Analysis script could, in principle, also be a few more lines. Depends a bit, but there should be, in principle, one script to say rule them all, and then you have some other steps described in a separate file. So this part I skipped till I think next week. So that was all for today. So thank you.